Hello everyone, I'm your instructor Dave Cocchiarella. This is chapter 13 from Essentials of Meteorology, the 7th edition, An Invitation to the Atmosphere. Of course, that textbook by C. Donald Ahrens. Chapter 13, Earth's Changing Climate. Not only chapter 13, but the last chapter of this coursework. We've taken a look at climate and climate classification and some of the larger scale and mesoscale features that create climates all over the world. But in terms of the global climate, there is an understanding among scientists that our climate is changing, but it's not all based on what's happening here on Earth with man and man-made processes. Much of the climate change we've seen over the globe during the globe's history over the 4.5 to maybe 4.6 billion years has all been very natural. So there really are two sides to this climate change controversy and conversation. So right now we'll take it into Earth's Changing Climate, Chapter 13 from Essentials of Meteorology.
In the study of climate change, it is important to understand that scientists understand that the climate of the Earth has always been changing. It has not been as it is today. As a matter of fact, largely, scientists believe that the climate of the Earth is quite a bit cooler than it has been for most of the Earth's history. And throughout the 4.6 billion years of the Earth's history, scientists believe that the climate has always been changing through natural processes. The question then for today is the climate changing also because of human activities? So let's first take a look at how we know that the climate has been changing. We have pretty good records going back 100 years in this country, 150 years up in the Northeast in New England, and perhaps longer in parts of Western Europe. But that's not the data that we use to know that the climate of the Earth has always been changing. We understand the changes based on natural processes we see at work today and proxy data. So this is the definition of proxy data from NOAA. Preserved physical characteristics of the environment that can stand in for direct measurements. So paleoclimatologists gather proxy data from natural recorders of climate variability such as tree rings, ice cores, fossil pollen, ocean sediments, corals, and other historical data. By analyzing records taken from these and other proxy sources, scientists can extend our understanding of climate far beyond the instrumental record. So what are those proxy data that scientists have used to reconstruct the Earth's climate going back many hundreds of thousands of years? One of them is glacial landscapes. So how do we know about glacial landscapes? We can look at what's left behind from glaciers, such as striations on the Earth's surface. We can also find very well-defined glacial sediment. Glaciers can move very large amounts of very large sediment, very long distances. And when those glaciers retreat and that sediment is deposited all at once in a location, it's an indication of glacial sediment. So glaciers and the existence of glaciers can be seen in the rock record. If we look at map A, that is the extent of glaciation about 18,000 years ago over North America, and B over Western Europe. And we can see those glaciers came all the way down almost into the southeastern states. And that last glaciation some 18,000 years ago, a very good indication that the climate, at that time at least, was much cooler. Another proxy data technique we have is long-range models, using computer models to do mapping and prediction, not only into the future, but into the past. And CLIMAP, which is the Climate Long-Range Investigation Mapping and Prediction System, does just that. It models the climate back into the distant past and into the future as well. There is lots of other proxy data, other techniques used to get direct measurements to give us an indication, an indirect indication of what the climate was like long ago. Ice cores taken from Antarctica can pull up ice from hundreds of thousands of years ago and give us an idea of not only what the climate may have been like, but also what the composition of the atmosphere. Dendrochronology, a fancy and long word for tree rings, and studying tree rings of some of our oldest trees like the bristlecone pine that can be found in the High Sierra, some more than 6,500 years old, giving us an indication of climates in the recent past. Lake bottom sediments and soil deposits can also be used to determine time frames and then what the climate may have been like in that time frame. Pollen in deep ice caves where ice was formed, again, thousands or tens or hundreds of thousands of years ago. The pollen that is found in that ice can give us an idea of the climate from long ago, as well as the soil deposits and also sea sediments. When we think about the sea floor and the abyssal plain where almost perfectly flat for millions of years, literally, sediment has rained down, 200 million years in the case of the Atlantic Basin, and longer in the case of parts of the eastern Pacific Basin. Sediment has rained down and collected on the seafloor. Those sediments can also be used to indicate what the climate was like when those sediments were preserved. We also find similar types of evidence in the change in water levels in closed basin lakes as the water level's gone up and down, indicating the change in the climate. Documents from the recent past, the concept of oxygen isotope ratios of corals with the heavier oxygen isotopes and the lighter oxygen isotopes, telling scientists whether it was cooler or warmer in the distant past. Calcium carbonate layers of the stalactites in caves using calcium dating methods to determine how old those stalactites are, and an indication of the climate with very, very wet and warm climates producing stalactites and very, very dry, cold climates not producing stalactites, and other techniques as well that exist in science to give us a very long-range view of what the climate has been like on Earth, and to verify that indeed the climate has always been changing on planet Earth. So here is a simplified graph showing geologic time from Precambrian through the Cambrian, and then of course through the Permian, Triassic, and Jurassic, Cretaceous, into the Tertiary, the Pleistocene, and the Holocene, where we are today. So this is going to go back some 570 plus million years, and what we see is before the Cambrian period, a faint and dim sun actually kept the Earth at a fairly low temperature, but as things progressed and oxygen began to build up in the atmosphere and carbon dioxides as well, the climate of the Earth was increased from about 12 to 15 degrees Celsius up into that range in and around 22 degrees. And only at very, very specific times where we see significant extinction events do we know that there were periods of heavy glaciation on the planet. And between the Ordovician and the Silurian, that's where we see a very, very cool period during the between the Carboniferous and the Permian period. We also have another cool period, and then a warmer Triassic and the Jurassic, some glaciation between the Jurassic and Cretaceous, and then from the Cretaceous to the Tertiary, then we see a big cool down to closer to where we are today. So much of the last 600 million years, the Earth is thought to be not only warmer, but in cases significantly warmer than it is today. And we have significant ability to reconstruct the Earth's climate over the last 18,000 years. And much of the last 18,000 years has been a period moving from an old ice age into the warmer Holocene period that we're in now. But there have been a couple of different pretty significant changes in the climate, such as the Younger Dryas, which was a significant cool down known as the Little Ice Age, and then the Holocene Maximum, where things warmed up significantly in the atmosphere. So even in the last 18,000 years, there's been dramatic changes, warm to cold, in the climate of the Earth. And these climate changes, we know, were not a function of man-made processes. We know they're a function of natural processes, and that gives us an idea of the extraordinary ability of natural processes to change the climate on the planet. Even in the last 1,000 years, we see some dramatic changes in the overall global temperatures. The medieval climate optimum between about 950 and 1200 it was a period of fairly warm or even warmer than current temperatures across Western Europe. And then we moved into what is known as the Little Ice Age, which moved from about 1400 to 1800, where temperatures were significantly colder. And then, of course, we get into the 1860s and the Industrial Revolution and the advent of the burning of fossil fuels, widespread, and then we see the increase in temperatures that we have seen in the recent 150 to 200 years. Here we're looking at temperature trends during the last 100 plus years and essentially indicating an average global surface temperature rise. However, not in a uniform way. When we look at temperatures over North America, actually, and likely because of pollution, we've not seen a similar temperature rise in North America. So this is not a uniform temperature increase, but it is a trend that indicates an ongoing global warming increase based on the trend. So what we're looking at is the average temperature variations over the Northern Hemisphere for the last 100 plus years relative to an average between 1961 and 1990. That's the zero line. So the blues, basically that's data that was taken from tree rings, from corals, from ice cores, and from historical records. The colors in red are actual data that were taken from thermometers, records taken from thermometers, and the black line represents the smoothing of that data. And we can see that moving into the 1800s, that we were below that average between 61 and 1990, but as we sort of moved out of the 30s into the 40s, we began to see peaks in temperatures, and then after about 1975, the temperature began to be warmer than the average of 61 to 90. But we can admit also that once we hit the year 2000, we began to see a slight tick down, but the overall trend does remain up. Having studied this extensively, scientists have come up with three significant mechanisms of the Earth's climate change. And those three separate large-scale mechanisms are the change in incoming solar radiation, the change in the composition of the atmosphere, and the change in the Earth's surface. So the change in incoming solar radiation, remember from our basic understanding of temperature, is the temperature at any given spot, and the reason for the seasons and for climate, for seasonal variability, is mostly due to how much incoming solar radiation strikes the Earth's surface, how much insolation. And so changes in insolation can change the Earth's climate. And now, having studied the climate significantly, scientists see that we have had periods of changes in incoming solar radiation. And those changes partially occur because of the Earth-Sun system and the way the Earth does move around the sun and how that movement changes over long periods of time. And those changes are cycles that are known as Milankovitch cycles. Mr. Milankovitch, probably Dr. Milankovitch, discovered and defined these. The other thing that we've seen with variability in insolation is sunspots. So with sunspots changing how much solar radiation reaches the planet. Now, the second and third mechanism are mechanisms that human activities can change, can have an impact on. Although they're not strictly human, both changes in the composition of the atmosphere and changes in the Earth's surface are largely natural. There are natural fluctuations in greenhouse gases, and those fluctuations in greenhouse gases actually tend to follow changes in climate, where warmer, wetter climates may produce the reduction of greenhouse gases through erosion, sedimentation, and lithification, basically taking carbon dioxide out of the atmosphere and locking it up in rocks. And then volcanism can increase the amount of carbon dioxide and methanes and nitrous that gets into the air through volcanic activity. So there are natural fluctuations in greenhouse gases, but there are also anthropogenic increases in greenhouse gases, and that's very easy to see. We can measure the increase in CO2. It's very clearly increased from about 280 parts per million to 380 to 400 since the Industrial Revolution. The question is, that increase in carbon dioxide, is it enough to move the climate in one direction or the other? And that's the question we're trying to answer. There also are changes in the Earth's surface. Now, large-scale changes in the Earth's surface occur through plate tectonics, and we know that 220 to 250 million years ago, most of the continents were stuck together in a supercontinent called Pangaea, and the location of the continents based on the actual surface of the Earth does have a big impact on the climate of the Earth. And so naturally, plate tectonics can change the Earth's surface to impact the climate, but humans can also change the Earth's surface through deforestation, urbanization, and desertification, and also the acidification of the ocean. So these are the three major mechanisms of how the Earth's climate changes, two of which can be directly impacted by humans. So I mentioned briefly a few moments ago a concept of feedback mechanisms. And a feedback mechanism is where a process serves to enhance the existing process, or a process may actually serve to decrease the existing process. And what we know is that no climatic element within the system is isolated from others, and feedback mechanisms can be either positive or negative. So a positive feedback mechanism is when the process causes more of the same process, and a negative feedback mechanism is when the process reduces the same process. And so first we'll take a look at a couple of positive feedback mechanisms, and the water vapor greenhouse gas feedback is a positive feedback mechanism where an increase in temperature results in an increase in evaporation, resulting in an increase in water vapor, which not only is a greenhouse gas but is probably the most important greenhouse gas. And so that increase in water vapor is then going to result in a further increase in temperatures, and that is a positive feedback mechanism. Now, that increase in water vapor can have other impacts, such as helping to create clouds that may have a negative impact on surface heating. So again, there's many subtleties and no straightforward one-to-one ratio between greenhouse gases and temperatures. So there's a lot of subtleties with these feedback mechanisms. There is the snow albedo feedback mechanism, which actually serves, in some cases, to cool the Earth, where the lack of snow serves to warm the Earth. So again, no climatic element within the system is isolated from others, and feedback mechanisms can be positive or negative. In this case, the snow albedo feedback mechanism is positive. In polar regions, as we see in the left, snow has a high albedo and therefore reflects a good bit of the sun's energy back into space. So there is low absorption of insolation. Low absorption of insolation results in very small surface warming. If the air temperature were to increase, let's say if the air temperature were gradually increase because of some other mechanism, the snow would melt. With snow melt, you'd have less sunlight being reflected, more reaching the ground, and more warming more quickly. The warm surface would then enhance the snow melt, which in turn would enhance the warming of the air. So the snow albedo feedback mechanism is a positive one. The way it can be a positive one but help to cool the Earth is increased snowfall, perhaps by a cool summer, where at northern latitudes not all the snow melts because it's a cooler than normal summer. That snow remains on the ground, and so the ground never warms up as much, which is going to result in a colder winter and perhaps more snow or ice formation that in turn reflects back more of the sunlight during the next spring and summer, resulting in another cool summer. So snow on the ground can feed back and cool the planet. Melting of snow, like the melting of the ice caps, which we've seen from satellite data, can actually help to warm the ground, melting that snow. Now a couple of negative feedback mechanisms. Infrared radiation is a negative feedback mechanism. This is subtle, but the heating of the Earth's surface will cause a geometric increase in the amount of radiation emitted from the Earth. And that goes back to, I think, Chapter 2, when we talked about Wien's displacement and Stefan Boltzmann, and we saw that the temperature of an object as the temperature of an object increases, the amount of radiation it emits increases by a factor of 4. It's raised to the 4th power. So heating up the surface of the Earth is going to geometrically increase the amount of radiation from the Earth. Well, we know that as the Earth radiates away its heat at night, that it causes it to cool. So since the amount of radiation absorbed from the sun would not increase during the day, but the amount emitted from the Earth would increase, the Earth would give up its heat more readily and then cap the heating surface. What we're saying is, in this situation, the Earth's not heating up because the sun's heating up. The sun's staying the same. The amount of insulation's coming in is the same. But if the surface of the Earth heats up due to global warming, one of these other mechanisms, the Earth is then going to literally radiate away at a factor of raised to the 4th power. The amount of radiation is going to increase, again, but the factor of the 4th power. And so it's going to geometrically increase the amount of radiation emitted by the Earth, which would cap the heating of the surface. So infrared radiation is actually a negative feedback mechanism. And then chemical weathering, I think I mentioned this before. A warmer planet, so this is a case where you've now had, let's say, global warming due to carbon dioxide, and we actually have a warmer planet. A warmer planet results in increased evaporation, condensation, and cloud cover, and then precipitation. But precipitation strips carbon dioxide out of the atmosphere through weathering of mountains, and then erosion, transportation, deposition, and lithification of those weathered rocks. And so you take the CO2 out of the atmosphere, you use it in weathering, you move all that downstream, and you have lithification of calcium carbonate rocks, sedimentary rocks. You've now locked up that carbon dioxide in the rocks. And that is a massive amount of carbon dioxide that gets sequestered underneath the ocean, not in the ocean, but underneath the ocean as sedimentary rocks. So chemical weathering is a negative feedback mechanism. An increase in temperature increases evaporation and precipitation, and an increase in precipitation strips the CO2 out of the atmosphere and locks it up as sedimentary rock. So as we're looking at our 3 major mechanisms for climate change, whether it's anthropogenic or naturally, we have to keep in mind these feedback mechanisms and how they may play out within these larger climate change mechanisms. So the first climate change mechanism we talked about was changes in incoming solar radiation, in insolation. And what we know, based on the Milankovitch theory, is variations in the Earth's orbit. This theory states that there's 3 different cycles with regards to the Earth-Sun system that result in a variation in the amount of insolation. You have the eccentricity of the Earth's orbit around the sun, which means the orbit is not always nearly circular like we are now. We're not a circle. We're a little bit of an ellipse, but it's not nearly as circular as it is now. It becomes more elliptical when there are points in which the Earth is further away from the sun and therefore not warmed as much. There's also precession of the Earth's axis, like a top. The North Pole doesn't always point at the North Star. It actually moves like a cone in space. And what that means is different sides of the planet are pointed toward the sun at different times of year, and that will change climate variability. And literally the obliquity of the orbital tilt, the tilt of the Earth is not always at 23.5. It goes between 21.5, and 24 to 24.5 degrees. And that also changes climate variability. So the eccentricity of the Earth's orbit around the sun, this change from a nearly circular orbit to a much more elliptical orbit takes around 100,000 years. Now, having said that, we do have some evidence that that change has taken almost significantly longer periods of time, but it is in that 100,000 year range for the Earth's orbit to stretch from a nearly circular orbit, which is the solid line in this illustration, to the elliptical orbit, the dashed line, and back, about 100,000 years. Now, remember, this is not to scale. The gravitational pull, mainly from Venus and Jupiter, but of other planets, causes the path of the sun to become slightly more or slightly less elliptical. When the orbit is more elliptical, the closest point in the orbit, the perihelion, is closer to the sun, and the furthest point in the orbit, or the aphelion, is further away from the sun. And what this does is, if you happen to be the hemisphere that is pointed away from the sun at the aphelion, then your winter is going to be much, much colder. And this type of variation in the Earth's orbit can have a pretty significant impact on climate, and combined with the other variations, when things all line up just right, can cause the Earth, one hemisphere or the other, to have colder winters, but also to have colder, that is, summers. And it's really the colder summer that's important, because it's in the colder summer that the snow doesn't melt, and the increase in snow on the Earth causes higher albedo and more sunlight to be reflected back, and for the Earth to continue to cool. So this is the first in the Milankovitch cycles, the eccentricity of the Earth's orbit around the sun. The second cycle is a much shorter time frame, somewhere in that 11 to 13 to 14,000 years, and that's the precession of the Earth's axis as it wobbles over this period between taking about 11 to 12 to 13,000 years ago in one direction, so a total period for the whole cycle of about 23,000 years. So right now, perihelion is January 3rd. So the northern hemisphere has a slightly milder winter, and the southern hemisphere has a slightly cooler winter. So half of that cycle, 12,900 years from now, the north will then have colder winters, because the Earth will be furthest from the sun in the aphelion in January. Another aspect of this precession is the length of the winter and the summer. So as our axis precesses like a top, or draws out this cone in space, it causes one or the other hemisphere to be pointed toward the sun at the aphelion or the perihelion, which changes how intense either their summer or their winter is. And again, it can push winters to be cooler or summers to be cooler, and it can also cause summers to be warmer and winters to be warmer. In the end, if they all line up with the other cycles, you have a cold winter and a cool summer, and you have snow that falls in the hemisphere and then never melts in the summertime, and again, that will allow the Earth to cool. The last of the Milankovitch cycles is the obliquity, or the changes to the tilt of the Earth. So our axial tilt is about 23.5 degrees right now. Over a 41,000 year cycle, it goes from about 21.5 to about 24.5. So 21 to 22 degrees, about 24 degrees. The change in the tilt of the axis controls seasonality, driving changes in the distribution of sunlight between the equator and high latitudes. More tilt implies more sunlight at high latitudes and warmer summers and colder winters. So our warmer summers and our colder winters will have one impact, then less tilt will result in a moderation of the season with warmer winters and cooler summers, and it's that setup that is thought to bring on glaciation. In addition to the Milankovitch cycles, for the first mechanism for climate change, we also talk about variations in the amount of incoming solar radiation in terms of the actual output of the sun. The solar output, the solar wind, solar radiation changes over time, and one of those things that's an indication of those changes are sunspots. Now, sunspots are essentially huge magnetic storms on the sun that actually show up as colder or darker regions on the sun's surface, and that's why they're called sunspots. And actually, there's an interesting cyclic nature of this, in that the maximum number of sunspots typically happens about every 11 years, and we can see by this graph at the bottom between 96 and 2008 how we had a sunspot maximum sometime between 2000 and 2002. In that time frame, we can also see the emitted solar radiation in terms of watts per meter squared of the sun increase as the sunspots increase, and then decrease again as the frequency of sunspots begins to decrease. And looking back and the climate over the last few hundred years, we do have records of a minimum, a period between about 1645 and about 1715, where there were very few sunspots. And in that same time frame, the climate of Western Europe was a little bit cooler than typical, as an indication of less solar output. So variations in solar output can possibly account for some climate changes, but we think it's a small enough variation that it really only accounts for small climatic changes. The second mechanism for global climate change is changes in the composition of the atmosphere. And again, this is one in which natural processes and human processes can have an impact. First, we'll talk about Atmospheric particles or condensation nuclei are just particles in the atmosphere, be they solid particles or liquid. They're microscopic. They're considered to be aerosols, and they enter the atmosphere from natural but also from human-induced sources that can have an impact on climate. Particles near the surface of the Earth actually will help to cool the surface of the Earth by blocking insolation. And particles in the upper atmosphere can have a significant enough impact in terms of cooling the surface that they have been responsible for mass extinctions in the past, hypothetically with the comet impact 65 million years ago. Another way that we see particles inserted into the atmosphere is through volcanic eruptions, and those eruptions tend to be rich in sulfur gases, which can produce a haze that will block insolation for up to several years. So atmospheric particles introduced into the atmosphere either by natural causes or human causes can serve to cool the climate, and that's one thing that we've seen in North America. We've not seen as significant of a climate increase, temperature increase as other parts of the world. Unfortunately, that's because of pollution that we also have over North America. Particles that end up in the lower parts of the atmosphere tend to be blown around and moved and don't have any type of real long-term impact on climate. However, particles that are injected into the upper layers of the atmosphere, particularly if they get up above the tropopause and the stratosphere, they can linger for several years, as is the case with this volcanic explosion. This is Mount Pinatubo in the Philippines. You can see this massive pyroclastic explosion eruption of this stratovolcano, and it put tons of sulfur up into the atmosphere, up into the upper levels of the atmosphere. And those atmospheric particulates were able to block the sunlight, creating a haze in the upper parts of the atmosphere that blocked the sunlight, that actually cooled the temperature of the Earth for a couple of years. And here we can see a temperature profile of between 1990, 91, and 92, where between 90 and the middle of 91, we did see a gradual increase in temperature, some fluctuations, but generally the trend was up. And then after Mount Pinatubo erupts, we have a fairly significant decrease in global temperatures. Changes in global air temperatures between 90 and 92 are shown on the graph after the eruption of Mount Pinatubo. In June of 91, the average global temperature by July of 92 had decreased by about ½ degree centigrade, or almost a full degree Fahrenheit, from the average between 1981 and 1990, and that average is that dashed line that you see. So the injection of aerosols into the atmosphere, whether they're by man-made causes or by natural causes, such as in volcanic eruptions, that can actually serve to cool the climate, to cool the globe. Some of these aerosols, some of these particulates injected into the atmosphere, of course, are going to come from human-induced sources. What are those going to be? Basically what you think they would be: emissions from factories, automobiles, trucks, aircraft, power plants, home furnaces, and fireplaces. And many of these particles do block the sunlight and cause a net cooling at the surface. Now, the flip side of that is the introduction of greenhouse gases into the atmosphere, whether that's natural or human-induced. An increase in greenhouse gases, carbon dioxide, water vapor, methane, nitrous oxide, can all serve to absorb outgoing terrestrial infrared radiation and warm the climate. And so when we talk about global warming and when we're dealing with anthropogenic climate change, the main concern we're talking about is this injection of greenhouse gases into the atmosphere because of human-induced sources. The third mechanism for global climate change is the change in the Earth's surface. Now, we have talked at great length about plate tectonics, about the breakup of Pangaea 200-some million years ago, splitting into the continents that we know today. And at different times during the Earth's history, those continents being at different places on the Earth, on planet Earth, have caused the climate at times to be warmer and also have caused the climate to be colder. And of course, changes in the Earth's surface based on plate tectonics is not something that man has any control of. But we do have control of land use, and land use changes has created modifications of the Earth's surface that have influenced the immediate climate of certain regions. We've seen a change in the rainfall in the Amazon River Basin from deforestation. Tropical rainforest clearing in and of itself puts excess carbon dioxide into the atmosphere. Urbanization causes the urban heat island effect, where concrete areas and lots of people and lots of buildings and lots of vehicles keep an area much, much warmer than they may typically be. And then desertification, the overgrazing and excessive cultivation of grasslands in semi-arid regions will cause an increase in desert conditions, and you get land that was usable becoming not usable because of desertification and poor cultivation practices and poor grazing practices. One of the things that we see when we see the introduction of greenhouse gases into the atmosphere is more and more of those greenhouse gases get into the world's oceans, causing not necessarily land use changes, but a change in the ocean, the acidification of the ocean, and that has a dramatic impact on the ocean itself and the very tenuous life forms that happen to live in the ocean. So this introduction of greenhouse gases into the atmosphere through human processes is referred to as a radiative forcing agent. We're putting greenhouse gases into the atmosphere. Composition of the atmosphere is one of the mechanisms for climate change, and so by putting greenhouse gases into the atmosphere, we are affecting one of the radiative forcing agents, increasing concentrations of greenhouse gases that disturb the radiative equilibrium. With the planet, with the composition of the atmosphere that it has now, with the amount of incoming solar radiation and the amount of outgoing solar radiation, the planet receives the radiative equilibrium level of about 59 to 60 degrees Fahrenheit over all places at all time. That increase in greenhouse gases would be thought to force that radiative equilibrium number higher, and thus global warming. Climate models have shown this trend not only recently but over the last 100 to 200 years, but it is still very difficult to unequivocally prove that the Earth's present warming trend is due entirely to increasing concentrations of greenhouse gases. We can see very clearly there have been significant warming and cooling trends in the past, and because of feedback mechanisms and a difficulty in putting the entire globe into a laboratory to do proper measurements, it's very, very difficult to prove absolutely that our current warming trend is due entirely to greenhouse gases. Clearly, they are a radiative forcing agent, but are they responsible for our current global warming? There are lots and lots of different projections as to where we are headed due to this anthropogenic increase in the concentration of greenhouse gases. What will it result in terms of additional global warming at the surface? Is it going to be something where we're talking about half or degrees Celsius, or are we talking about several degrees Celsius? And most of our current projections do fall into that several degrees Celsius range. Now, there are uncertainties about greenhouse gases, the effect of water and land on rising levels of CO2 and the amount of greenhouse gases. Some of those negative and positive feedback mechanisms, how do they equal out to really determine how much CO2 is in the atmosphere? There continues to be the question of clouds and how clouds reflect radiation and also emit infrared radiation. What is the net effect of the clouds? And also, what is the ocean's impact? How much CO2 can the ocean absorb? How much can the ocean buffer global warming by absorbing some of that heating without completely destroying the equilibrium of the ocean? So climate projections really are tentative, and each model is based on the inputs and then the parameterizations, or how they model the effects of different things. And because of the differences in those modeling techniques, we get lots of different answers in terms of the projections for global climate. So one thing that we have been very effective at measuring, and something that we can show very clearly, is the amount of the greenhouse gases. How much carbon dioxide, how much methane, how much nitrous oxide has there been in the atmosphere, and how much is there now? And so the graph on the left is what is known as the hockey stick. And of course it's called the hockey stick because if you set it on its side, it looks like a hockey stick with this dramatic increase in parts per billion or parts per million of carbon dioxide, methane, and nitrous oxide as we look at literally just the last 200 years. And we can see separated the carbon dioxide, the methane, and the nitrous on these charts on the right-hand side. And these are direct measurements. These are not proxy measurements. These are direct measurements that have been taken in the last really 50 to 60 years. And prior to that, a lot of the data is proxy data. But scientists have a very solid understanding that this is the type of increase in greenhouse gases that have occurred since the last 2,000 years. Here is an illustration representing data from a number of different types of global climate models. Now the baseline is going to be the temperature average from 1980 to 1999. And then we see the historical data in black from about 1950 up to just after the turn of the century. Everything else is going to be model data projecting out to the year 2100, and then we also have additional model data on the right-hand side, the RCP 2.6, the 4.5, 6.0, and 8.0. And each of these different model outputs is based on different parameterizations or different initial inputs in terms of the amount of global greenhouse gases that exist. The one thing that is worth noting is that one model that does show in the orange shows what the temperature would be if the greenhouse gases are held constant at the year 2000 level. So what's important to see in this is in some cases we see about a 1 degree Celsius temperature increases, and in other cases we see upwards of 4.5 degree temperature increase. So there's a wide margin involved in this, and we do know that the Earth naturally fluctuates around a mean within a degree or two. So perhaps this is extreme, perhaps it is not, and again the ultimate outcome can only be seen with time, but this is more of the data that climate scientists look at regularly to determine what the exact causes of current warming trends are. The consequences of climate change, whether those changes are forced anthropogenically or naturally, of course land areas are going to warm more rapidly. So if the overall globe is warmer, that means temperatures on land are going to heat up more rapidly, cool off more rapidly. Additional CO2, in and of itself, CO2 is a dangerous gas. Too much of it can have a negative impact. We see that out the High Sierra near Mammoth Mountain, where CO2 seeping through the ground from volcanism below kills the trees. We're definitely going to sort of change our precipitation patterns if we see ongoing warming, and very likely that if the global ice caps continue to melt, and of course they've melted and grown many, many times in the past, but we will see a sea level rise. Now, for the state of Florida, we can look at fossilized sand dunes across the state and see that at times sea level of the Florida platform was much higher, leaving only things like the Lake Wales ridge exposed above sea level, and we can also see periods where sea level was much lower, where the entire Florida platform was exposed, making Florida some 300 miles wide. So sea level change certainly has occurred in the past because of natural forcing agents, and certainly will continue to occur if warming continues to occur. What happens at the poles becomes very, very complex. Now, one of those negative feedback mechanisms, an increase in CO2 is essentially fertilizer for plants, and plants are going to take in that. More plants will take in more of that CO2 and maybe begin to sequester that CO2 in different ways. So again, it's very, very complex. There's no certainty in which direction we're going, but the more we understand, the more we can be prepared for some of these large-scale changes. As we discussed on our discussion boards, what efforts can be made to curb climate change, to curb the change in our average global temperature? We're real happy with it at 59 degrees Fahrenheit, not so happy at 60 or above, maybe even down to 58 or 57 to allow those ice caps to reform might even be better. So what can we do to curb climate change in the wrong direction? Well, the first and most obvious is going to be the reduction of greenhouse gas emissions by the reduction of fossil fuels. And we can look at that and say, well, let's legislate that. But I think, in my personal opinion, the legislation of those types of rules globally extremely difficult. And this is where the concept of developing an energy ethic, a global energy ethic, where the use of alternative energies becomes more prevalent and the use of fossil fuels diminishes. And of course, as we all know, the fossil fuels, there's a finite amount of fossil fuels available. So why not use energy in which there's an unlimited amount, at least for the next 4.5 billion years or so, which would be solar energy or even wind energy? Because remember, winds are essentially created by pressure patterns. Those pressure patterns are created by changes in temperatures across the globe. So ultimately, even the wind is a function of the sun. Back to legislating changes, the Kyoto Protocol, which is essentially passed at this point, set mandatory targets for reducing greenhouse gas emissions. 160 countries agreed. Very few actually met those. California, interestingly enough, implemented the protocol all on its own. Geoengineering as another attempt to curb that. Global scale technologies to fix and fixes to counter climate change. What are those? The book describes them. Do we put big mirrors in space to block incoming solar radiation? Do we try and force more gases into the ocean? Lots of different ideas on global scale technological fixes. But you always have to ask, what are the unintended consequences? Because there always will be unintended consequences. A final note from the author of our textbook, cutting down on emissions of greenhouse gases and pollutants have several potential positive benefits. The slowdown of the enhancement of the Earth's greenhouse effect and the reduction of global warming, and also the reduction of acid rain, less haze, and slowing the production of photochemical smog. So I think this is sort of a statement reaching out toward that concept of this is beneficial. Making these changes is beneficial. Good stewardship of the planet is beneficial. Creating a global ethic on energy, on water, and land use, not legislation, but an ethic that the entire globe shares, would be beneficial in preserving our resources and cutting down on the negative impacts of industrialization. And so it's pretty easy to see that less pollution is better. It's much more difficult to achieve that goal.
All right then, that is Chapter 13, Earth's Changing Climate from Essentials of Meteorology, a conversation about natural global climate change and potentially even man-made global climate change. That does wrap up this coursework for Introduction to Meteorology. I'm your instructor, Dave Cocchiarella, and I hope you got a great deal out of the course. Don't forget, if you ever have any questions now or in the future, please feel free to email me, and good luck in your future studies.